Yes, we can.
Last, a previous lecture, we had Excision Theorem, which I didn't completely prove, but like if you're interested in the proof, you can, for example, watch in a more detailed proof. You can watch, for example, videos of the previous year. But I omitted, essentially what I omitted were some kind of technical details. And okay, so in one of these formulations, the theorem tells us that okay, if we have a triple of topological spaces.
Excuse me.
Yes.
We can't see the blackboard.
Oh, you can see. Okay, good. Well, let's wait a bit. Okay, now I think you can, right?
Yeah.
Okay,
Yes.
thanks.
Now it's okay.
So you had a triple of topological spaces, so that and you also have additional kind of condition that the closure of Z was inside A. And then if you consider it the homology group, nth homology group of X relative to A, to the subspace A, you could kind of excise from each of these spaces these smaller subspace Z. And you get an isomorphic group. And as promised, we want to kind of use it to obtain a relation between relative homology groups and homology groups of the quotient. But before we proceed, it's kind of useful to introduce the following kind of modified definition of the homology groups, which also quite often used in the literature. This is what is called reduced homology groups. And they are defined as follows. So this is a very slight modification of the usual homology groups, but using this reduced homology, it's often easier, kind of nicer. Some statements look nicer, more compact. So to do this, consider what is called augmented singular chain complex. So let's consider the same thing as we had before, just the usual chain complex where the groups here appearing are the groups generated by groups of singular chains in X. So these are our boundary homomorphism. And before we had, so we considered that this the next D here takes us just to 0. But we can consider a slight modification of this place and consider instead a certain map epsilon, which will take us to Z, and then the next map will be just a 0 map. It will take us to 0 loop. And this will be, epsilon is defined as follows. So here, an arbitrary element here can be represented by a linear combination of singular 0 simplices. So this is each of these guys is just a map from a delta 0, which is a one-point space, to our X as usual, and we map this linear combination to just integer, which is the sum of the coefficients. So this is actually, we already considered this map when we showed that we already considered this exactly this map epsilon when we showed that the H0 of a path-connected topological space is isomorphic to Z. Okay, and so we define. Then what we say is that so it's easy to see that this is still chain complex because the kernel of each map is contained. So the image of the image of each map is contained in the kernel of the previous map. So here, for example, we know. So this is still true here. Well, this is obviously true here because the kernel is everything, and this is still true here because, again, as you remember from, for example, from this proof of the statement about H0 of a path-connected topological space. So any singular, if you consider an arbitrary singular one simplex here, which is essentially a map from an interval to a topological space X, this boundary will give us a linear combination of its boundary points with signs plus and minus 1. So and then for any linear combination, of course, the singular chains which can appear here, they will always have it will always be such that the sum of coefficients is 0. So indeed, the kernel of this map contains the image of this D. So this is still satisfied. Let me explicitly write this as a D1 as before, and this was D2. So kernel of D1. Sorry, what I want to say is kernel of epsilon contains of D1. So, and therefore one can consider, as for general chain complex, one can consider homology as a corresponding homology group, just defining the nth homology as a quotient of kernel over the image. Let me write it here. So its homology, the homology of this chain complex, as we just considered, its homology groups are what is called reduced singular groups of topological space X. So this is a definition of reduced homology groups, and they are denoted usually as H tilde of n of X, so just add a tilde. And of course, from the definition, it's as clear that well, for n for n greater than 0, they are just the same as nh of X, because this is, as before, this is just a kernel of dn divided by image of dn. So you don't, nothing is affected at all. So if you look at this modified single chain complex, nothing is modified for indices greater or equal than 1. So the only modification happens here. And here, and for n equals 0, well, for n equals 0, you get, well, from definition, you get a kernel of epsilon. So instead of d, you have epsilon, and divided by the image of d1. But it's easy to see that this is always isomorphic, although not canonically, but it's isomorphic to the unreduced homology group in degree 0 quotient by z. So how can one see this? Well, this is just because, so what was unreduced homology group? HF of x. So this was just the whole C0 of x, on which in the non-reduced, non-augmented chain complex, D0 was 0. So the kernel was, in this case, was just the whole space C0, and we divided by the image of 1. And as you remember, one can consider, so this group is isomorphic to a direct sum of copies of Z over all path-connected components, path components of X. And more precisely, each of these Zs can be understood as generated by the class of sigma alpha, where sigma alpha is a map from delta 0 to X, such that its image, of the sigma alpha is contained in a particular path-connected component. Path component. And since here, instead of, so for H1, sorry, for H0 tilde of X, instead we have a kernel of epsilon, which is a subgroup in this C0 of X, divided by the same D1. And from this description, you can see that this is just can be understood as a kernel of this map epsilon acting of this kind of kernel of the induced map, or denoted as epsilon star, for example, which epsilon star is a map from H0 of X, unreduced homology group to Z, and it just takes, so here an arbitrary element, again, is can be written of this form. Sum of path components of X, and for each path component there is a corresponding generator of this unreduced homology group, and we consider it with some integer coefficient, and this is mapped to the sum of alpha. And then essentially so the kernel of epsilon star is can be understood as a subgroup, is a is a subgroup in H0 of X of elements of the form we have this sum so that the sum of the coefficients is 0. But of course, we can always so it's kind of it's obvious from this that it has just one less generator. So you can always consider. So it has one less generator, so you can. So it's isomorphic to H0 of X divided by Z. So more explicitly, you can, if you wish, you can consider, for example, consider particular isomorphism between, so let me consider the following. So fix some particular path component which has index beta, and then let's take x0, some point in this path connected component. Then we want to construct isomorphism between H0 x comma x0, which is a relative homology group. And this reduced homology of X just by taking, for example, here, so here have an arbitrary element looks like this, so it's sum over generators corresponding to all path connected components, so that the sum of the coefficients is 0. You can map it to an element here, so that you have a sum of you just can take the sum over all guys excluding beta. So this is because this group, as we know, is is generated by it's it's generated. It's exactly generated by all these singular simplices corresponding to path connected components, excluding this beta. So what I'm saying, if you schematically represent your X like this, and you put some point of fix some connected component beta, and there's a point x0 here, and you consider relative homology with respect to this x0. So you quotient, in particular, you quotient over all maps which map to x0 and which are homologous to, of course, homologous to all maps with the image in any point. Connected components. Anyway, the conclusion is that this is, and this group, we know that it's, this relative homology group is isomorphic to this sum over all path connected components excluding not equal to beta, and which can be written as a kind of H0 of X unreduced divided by Z. So this Z is corresponds to the generator to the generator corresponding to a path-connected component containing this fixed point x0. This isomorphism, there is such isomorphism, but it's non-canonical in the sense you have to choose one path-connected component. And the inverse map, of course, you can construct. Well, just taking, okay, you have here, you have a sum of all components excluding beta, and here you map it to the sum where you take this sum over alpha not equal to beta of the same thing, the sigma alpha, and plus you add this generator corresponding to plus component beta with coefficients being minus sum of the coefficients. Here, yeah, in all these cases, my beta is fixed, but alpha is what I used summation. And so in particular, for example, in this, we consider reduced, so unreduced homology of a one-point space. It was just z when n equals 0 and 0 otherwise. For reduced homology group of points is just 0 everywhere, because here so the difference between reduced and unreduced homology group is that just you remove a copy of z at degree 0, and you don't do anything else. Pretty mild modification. Any questions? And for relative homology groups, in principle, you can also formally consider the reduced versions, but you just say that they are the same as unreduced for any index. Okay, so why this is natural? Well, this is because of the following. So we have still, so suppose that we consider augmented chain complex for this subspace A in X. So we augmented it by this copy of Z here. And then similarly for X here. And then we had the chain complex of relative chains, C0 of X divided by C0 of A at this part. So we don't modify anything before this. And so okay, so here these all rows here, we want them to fit, all columns we want to fit into short exact sequences. So this map is just inclusion, and this map is quotient. And so it's natural to have the same thing, to have also a short exact sequence in this extended column. And here, if you want this all arrows to commute, here we want to make this also a kind of inclusion, which here is just essentially identity map. Because here, okay, here the result of this map is just sum of the coefficients of my singular simplices here, and here it's also sum of the coefficient. But if I consider this inclusion, of course this should be the same sum of the coefficients. So this should be just an identity, and then if I want this to have a short exact sequence, then it should be again a quotient map, but Z quotient over Z is a trivial group. So this we want to be 0 as before. So this for the relative homology, we don't need to actually modify everything. So if you want to still preserve the fact that this the triple of chain complexes forms a short exact sequence of chain complexes, and so we don't modify. So reduced, you can say that reduced relative homology groups, they're just the same, and then this statement about long exact sequence of reduced homology groups. Sorry, let me write the statement about a long exact sequence for a pair x comma a still holds for reduced homology. The only to show this statement to show that these the homology groups for a triple of chain complexes forms a long exact sequence. We only use the fact that we only use the structure that they all fit into this big commutative diagram, which we have here. Okay. Any questions? Okay, now we can make the following statement. Theorem. So let A be a subspace in X which is non-empty and closed. And moreover, additional condition that such that there exists neighborhood V containing this A and a V, and this V can be deformation retracted to A. So V deformation retracts to A. And in general, if you have a pair of topological space X and a subspace inside A, which satisfies all these conditions, so such pair X comma A is called a good pair. This is a definition we'll be using. Okay, so this is the conditions these are, which we want to impose, and then statement is the following. Then the quotient map Q. So I consider this, so my quotient, so I consider a quotient map from X to X quotient by A. And of course, I can consider it as a map between pairs. So because it will satisfy this condition that the image of A will be contained in this in the subspace in this pair here. So here we just quotient A with respect to A, and this is of course just a one-point space. So here, so as usual, this quotient means that we impose the equivalence relation so that X, so for a pair of point X1, X2 in X, they are declared to be equivalent if and only if they both belong to this subspace. So just kind of quotient is you collapse all points of the subspace A to a point. Just kind of shrink it. Okay, so the same as the quotient map. You can consider this quotient map as a map between pairs. And it induces the map between the corresponding homology groups, relative homology groups, as we know. And the statement of the theorem is that this map is an isomorphism. But of course, this is just a one-point subspace, A quotient over A. So it's just a single. All points are in the same class. Goodness class is just one-point subspace. So this is, as we know, relative. As we kind of just consider it, the relative homology group of a topological space relative to some point inside is isomorphic to what we denoted by reduced homology group. Again, this reduced is just a very simple modification. So for all indices n greater than 0, this does nothing. It's just the same as we had before. And for n equals 0, just removes a copy of z in your direct sum over path-connected components. And this is okay. This will provide us the desired statement about relation between relative homology groups and non-relative homology groups, but of some quotients. Okay, so how do we prove this? Consider first long exact sequence of homology groups for the pair V comma A. So V is our neighborhood containing A. So we knew that so A was a subspace in X, but there was a condition that A can always be included in some neighborhood V inside X. And so, of course, A can be considered as a subspace in V, and we consider relative homology groups for these pairs, and they fit into this long exact sequence as we had before. Okay, you have this for V, and then you go to the index changed by -1 and -1. Then you continue. So these two maps, they are just induced by inclusion, I star. And we know, so since V deformation retracts to A, the push forwards of the inclusions are actually isomorphisms. Because V deformation retracts A. Okay, and this means, okay, if this is isomorphism, and we know the sequence is exact. So in particular, the image of this map is the whole space. So this should be the same as kernel of this map. So the kernel of this map is the whole space. So this map is just trivial. And similarly, if you look at this part, okay, so this is isomorphism. So this means that the kernel is trivial here, but the kernel should coincide with the image of the previous map. So the image is trivial. This means that this is also 0. And well, this implies that this space itself must be trivial, right? Well, we know, for example, this. Well, we know that okay, the kernel of this map is a whole space because this is 0, but we also know the kernel should be the same as the image of the previous map. The previous map is trivial, so we conclude the whole space is trivial. Okay, good. So this is, okay, now we learned that these relative homology groups of V, A are trivial, so we keep it in mind. Okay, the next step is the following. So let's consider short exact sequence of chain complexes for the triple, sorry, for the pair X, comma V, right? So we have this short exact sequence. And we use the fact that V is the pair V in X. And what we can do here is we can divide everything by subgroup Cn of A, the chains, singular chains in A, because this is a subspace here, this is subspace here, and this is, of course, a well-defined subspace here, because this Cn of V is contained here. So this is actually, this is a trivial subspace here, because you already quotient with respect to all chains contained in V. But this is, of course, includes So this subgroup is a subgroup in C of V. So this quotient does nothing here, but it does something here and here. This gives you following new short exact sequence. Okay. And once you have a short exact sequence of chain complexes, this means that you have a long exact sequence of the corresponding homology groups. It induces long exact corresponding homology groups, namely for this quotient we have a homology group of V relative to A, and then we go to homology group X related to A, and then we go to the homology group X related to V, and then we use this general construction which tells us there is a connecting homomorphism which takes us to Hn minus 1, V comma A, and then we continue. Okay, so this just takes us here. Okay, and again, well, we already learned that these groups are trivial, right? From previous consideration, we learned that this is 0 and this is 0. So this means that this map is necessarily trivial and this map is necessarily trivial. And we already know that if there is either kind of two groups, we have two abelian groups, consecutive groups in our chain in any exact sequence, and they are sandwiched between trivial maps. This map between them is necessarily isomorphism. We already showed it in general situation. So this is isomorphism. And let me denote this isomorphism by some concreteness. So let me denote this map between this chain map F and the corresponding isomorphism of the homology group as F star. Any questions? Okay, good. We know that this V deformation retracts A, and these were subspaces in X, right? And well, similarly, you can say that if you consider if you quotient everything with respect to A, to this equivalence relation which identifies all points in A, you immediately get the fact that V quotient by A deformation retracts to A quotient by A, and this is understood as a subspaces in X quotient by A. So just use all maps, all these retracts and homotopy between retract and identity, compose it with your quotient map, and you immediately get this statement. And this is, of course, a one-point space. There is one equivalence clause here. And okay, so here, so we made some we made some analysis for this triple so made some statement. We consider this triple of A, V, and X, assuming that V deformation reacts to A. So we made some analysis and we concluded that these the certain homology groups are isomorphic, and we can do the same analysis for this triple now A comma A. So repeat this analysis for the triple where everything divide by A. So it still satisfies these conditions which we used here. And so in particular, to follow that, so as we showed for this triple, we'll now have that the homology group X divided by A, comma A divided by A will be isomorphic to HN V, so X, again, X divided by A, but instead of A divided by A, we have V divided by A. And we'll let me denote this map is also as F star here. So again, I kind of abuse my notation, use the same notation as here. So here we had a homology of X relative to A, isomorphic to homology of X relative to V. And now we just do the same thing, but we quotient everything by A. This respects all the conditions which we had, and we get this isomorphism for between these spaces quotient, homology of these spaces with quotients. Okay, good. Okay, now let's combine everything what we learned in a certain commutative diagram. Okay, good. So okay, so first thing we learned is that Hn x comma v is isomorphic to Hn A, some particular isomorphism which we denoted by F star. And we also noticed the same thing when we quotient everything A. Here we also denoted this same symbol, star. Have the same thing as in the first row, but spaces are quotient by A. And then, okay, so we have from here to here, we consider our Q star, which we defined formulation of the theorem. So Q is a map induced from by the quotient. So this is Q is a quotient map. The maps X to X divided by A, and of course it's it can be extended to the map for the pairs. So you consider any subspace, a pair of X and any subspace inside the quotient on this subspace. And similarly you have here, right? You can consider a quotient map for this pair X, comma A. There will be a corresponding induced map Q star for these homology, relative homologies here. And now we want to use the excision theorem. So let's notice that we can use this triple A included with V included in X satisfies the assumptions of the excision theorem. So assumption of the excision theorem was that the closure of A was inside V. But A, in our assumption, A itself is just closed already. So there is no issue here. So excision theorem tells us that there are isomorphism between this relative homology group for this pair and where we excise this A from X and V. Complement of A spaces, and this is just, as you know from the excision, this is just the map which provides isomorphism is inclusion of this complement in the original space. And similarly, we can have this. We have considered the excision theorem of downstairs, right? So for here, we use excision theorem for the triple. Again, where everything is just divided by A. And here, okay, if you consider this complement and consider quotient of the complement, is the same as making a complement of the quotients, right? You can instead instead of taking the complement of this subtraction, you can of spaces, you can consider X divided by A minus A divided by A, right? And here, B divided by A minus A. Okay, and and you of course can consider, this is also the map induced by a quotient map between this pair of homology groups. And here you can see actually this map then well, you can see that this kind of tautological way. Okay, let me denote this. Okay, so I used kind of the same notation Q, but let me actually distinguish them somehow. Let me denote this map as Q double prime star, and this is Q star prime. So just to distinguish that they are between different groups. So let me first make the following observation, that this Q star double prime is an isomorphism. Well, this is just actually not just isomorphism, it's just identity, because you can see that what you do here is actually you do nothing, because when you consider this quotient. Because okay, quotient, what does the quotient mean? Quotient means identifying points which belong to A. But if you removed already A from everywhere, this does nothing, right? You don't have to identify. So this, these topological spaces, they're just the same topological spaces. Also, you write it like this. Okay, and okay, so and the second observation is that this diagram is commutative. Is commutative. Well, it's kind of, so why it's commutative, for example, here? Well, this is just because these, these maps here are just induced by some geometric maps defined in terms of topological spaces. And so these maps here, they are just induced by inclusion, and these maps are induced by the quotients. So we know already that the corresponding maps within the topological spaces, these quotient and inclusions, they commute. And therefore, the induced maps also commute. So here, okay, these maps are not quite geometrically defined, F star. So we have to kind of think a bit why this is commutative, but it's also more or less tautologically. So let's look about how these F stars are defined. So F stars are defined by just quotienting so this, so how you obtain, okay, if we return back to what we had here, that we see that this F, well, it was induced by the map which we have here, which was just a projection map. So you quotient over all chains contained in V. And you do the same thing here, but you already quotient. You first quotient with respect to all chains contained in A, and then you quotient with all chains contained in V. And of course, and then, so this is for a map here, and here you do the same thing, but you first, but you do this on the quotient on these, on the same thing, but for the topological spaces quotient with respect to A. And of course, it's, so here it's easy to, so you can consider this map quotient induced on the corresponding chains, and it's easy to see that, well, the corresponding maps on the chain complexes, they obviously commute, because you can first, you can compose, so this kind of, the quotient map just induced on the chains, it just acts by composition, and this composition is again commutes with this taking the quotient over some subgroup, because this, all these quotient maps, they respect these inclusions which we used here, the inclusions of the corresponding subgroups of the singular chains. So here this also commutes, and well, if you have a commutative diagram where this is isomorphism, this is isomorphism, this is isomorphism, and this is isomorphism, and this is also isomorphism, this necessarily implies that every row here must be an isomorphism. So this might be an isomorphism because we can just go this way instead and get an isomorphism. And then this implies that this is also isomorphism because you can also go this way and get an isomorphism. So everything is an isomorphism. And okay, maybe okay, this was actually my original Q star, which I wanted to consider, and this is, let's say, Q prime. And okay, so again, from the fact that this is a commutative diagram and this is isomorphism, this is isomorphism, and this is isomorphism, we necessarily get that this should be an isomorphism. Okay, so Q star is an isomorphism. And this concludes the proof. So this is what we wanted to show, that this Q star is an isomorphism. Any questions? Then we can formulate the following, immediately we have the following corollary. For a good pair, what is good we defined in the previous theorem, in the definition, in the formulation of the previous theorem. The good pair X, A. There is the following long exact sequence. Of, again, for convenience, we use just reduced homology groups. We go first like this, and then you continue homology group with index n-1 till the end, and you finish at h tilde 0 of x, and then you go to 0. So this corollary immediately follows from the statement which we just proved, and as a statement that about isomorphism between the relative homology group and reduced homology groups of the quotient. Again, this reduced again just matters at index 0, where it's we use the fact that the reduced group is just isomorphic to a group relative to a single point. So this gives us a statement, just a statement about non-relative homology groups. In particular, if there may be, it may be used to kind of if some of these, in some of the places in this sequence we know the groups, you can use exactness to deduce the groups in the other spaces. So let me consider the following example of how this fact can be used to do some calculations. So let's consider a situation when X is a n-dimensional disk or a ball, if you wish. Depends. Preference, and A is a subspace which is its boundary. So this is a closed. I take a closed disk, and boundary. But the boundary of this n-dimensional disk is, of course, n-1 dimensional sphere. If, for example, if n equals 2, you have this is your x, and A is a boundary. And it's of course, it satisfies, well, in general, you have some, like in angle 3, you have a ball, and the boundary is 2 sphere, and so on. And it, of course, satisfies this condition. There exist, this is a good pair because there exists a neighborhood V. Which contains your A. Just take V to be a complement of a bit smaller disk or ball. And again, depends on the dimension. Okay, so this pair is good. And okay, and what about the quotient? The quotient, you need to consider this disk, and you want to identify all points in the boundary. But this space is homeomorphic to n-dimensional sphere, right? For example, if you in this case n equals 2, if you identify all points on the boundary, this is you can imagine some sort of you get essentially sphere, you kind of collapse everything to a point, and this point is just one point on this sphere. Okay. Okay, so and what is the long exact sequence which we have? It looks like this. So consider, okay, so this the triple, how it goes, it's A, then homology group of X, then a homology group of the quotient, and then we return to homology groups with index reduced by 1. So homology group, so A is isomorphic to n-1 dimensional sphere. And so this is our And then we go to a homology group of X, so n-dimensional disk. Then we go to homology group quotient, which is can be identified with n-dimensional sphere. And then we continue. Next row is the homology group again of n-1 dimensional sphere. And then again homology group of disk, so on. Well, the disk, okay, we know that the disk is a contractible space. So it can be deformation retracted to any point inside, for example. So this is group is trivial, and this is also trivial. In particular, this map is zero map. This map is zero map. This is a zero map. Okay, good. And now we look at this segment of the sequence from this to this, right? So we know again that if it, is there some question?
No, it's isomorphism then, because it's exact sequence. This part is short exact sequence.
Yes. So yeah, yes. As you know, you have a pair of groups sandwiched between zero maps. The map between them is necessarily an isomorphism. So what we learn is that H tilde k of n is isomorphic to H tilde k of S minus 1. And this essentially tells us that if we know the homology group of n-1 dimensional sphere, this will tell us what is the homology group of n-dimensional sphere. What is the homology group? What is the sphere for which homology group we actually already know? Well, this is a zero-dimensional sphere. The zero-dimensional sphere, well, this is a disjoint union of 2 points, right? Of two, yes. Well, is there, I mean, if you're not happy about this, I mean, their statement, there are various ways to see this. This is a boundary of a one-dimensional disk, which is an interval, so it's 2 points. Or it's a solution of equation absolute value x equals 1 in one-dimensional Euclidean space. Okay, and well, we know then this tells us the homology group of S0. So this is disjoint union. It's a direct sum of homology group. So it's a disjoint union of two spaces. This is HK.
Z plus T. Z plus T.
HK point, yes, and each of them is just 0 when k equals 0 and 0 otherwise. So this is z squared when k equals 0 and 0 otherwise. Again, this this has two generators corresponding just to these two connected components, and alternatively, you can use the relative homology group. And again, the relative means, reduced homology groups. And reduced again means that only in degree 0, when k equals 0, we remove one copy of z corresponding to either of these connected components. And so we get, so for reduced, we get just one copy of z when k equals 0 and nothing, well, trivial group otherwise. Okay, so these are, so we know, so these reduced homology groups are simple, and then we from this, so it's 0 unless k is the same as the 0 here, and this means that from this relation it follows for general n now that hk of n, the relative is isomorphic to z when k equals n and 0 otherwise. Again, this relative homology group do not contain any additional information, so you can immediately, I mean, you also, this immediately tells you what are unreduced. So what you want to do is that you want to add a copy of z. Well, suppose this is for n greater than 0 now. Okay, for s0 we already know everything. Then what you want to do, you want to add a copy of z for k equals 0, right, to recover unreduced. Oops. So then the answer is z when k equals n for 0, and it's 0 otherwise. So these homology groups, it's only have a single non-trivial generator in degree 0 and in degree n, which is the same as dimension of Sn. Morally, you can geometrically you can understand this so kind of what is the singular chain which generates z here in n dimension. So this is, for example, again when n equals 2. You consider a certain, well, because we consider triangulation of the sphere. And this triangulation gives you, can be understood as a singular two-chain, which is not a boundary of any singular n+1 dimensional chain. So kind of a minimal triangulation, you can, for example, choose just two triangles, or you only care about kind of two triangles, kind of taking a sphere. Well, this is in n equals 2, for example, how you imagine. You just choose kind of two triangles with vertices on equator. This can be understood as just covering your sphere by two triangles. Well, it's kind of not kind of not your usual triangles, but that's okay. Any questions? Maybe I have time to quickly tell about some other application. So they can be actually formulated as not just kind of example, as some sort of theorem about invariance of dimension. So let U be a subspace in Rm, and V will be subspace in Rn, and we assume that they're open and non-empty. And then under this assumption, we want to show that if they are homeomorphic, this implies that the dimensions are necessarily the same. So intuitively, it's kind of obvious statement, but well, how do you actually prove this? Well, how do you prove there is no, for example, homeomorphism? Euclidean spaces in different dimensions. So what is the proof? So let's take some point. So it's a non-empty. U is non-empty, so let's take some x in U, and we can use so by excision theorem. We can notice that if we consider the following relative homology group of U relative to U with this point removed, it's isomorphic to the relative homology group of Rm, where U is our subspace, relative to, again, Rm with just one point removed. So how this fits into in our general statement of excision theorem? Well, you take this to consider the triple, where this is your X, and this is your subspace A, for example, in X. And here, what you want to excise, you want to excise Z, which is a complement of Rm minus U, which is indeed the closure. You have this condition, the closure of Z is included in this A. And then if you excise this Z from each of them, you get what you have on the left-hand side. This is X minus Z, and this is A minus Z. And now let's consider for this pair X and A, which we have on the right-hand side, let's consider a long exact sequence. This is sequence, long exact sequence for our pair Rm minus point. Okay, so, and let's see. How does this go? So, okay, HK, and we have HK Rm minus X. Then go to HK Rm. Then you go to relative. And then you start repeating, but you reduce degree by 1. Do dot. And of course, you can use, as I mentioned, you can use the relative groups so that, well, it only will matter if this K, for example, is 1. So then the reduced group will affect your homology in degree 0. Okay, so this we know. So Rm is homotopy equivalent to a point, right? There can be deformation right to a point. So you get here, you get a reduced homology group of a point which are trivial in all degrees because they are reduced. And then again, you have this is 0. Maps is 0, so this must be an isomorphism. But for this guy, we know that this space Rm minus a point is homotopy equivalent to m minus one-dimensional sphere, right? Because if you consider Rm and you remove a point, so for example, consider a sphere which surrounds this point, and you can then once you remove the point, you can deformation retract the complement to the sphere like this. So you just do this retraction along the rays in this radial direction. So outside of the sphere, you retract towards the sphere, and inside the sphere, you outside. So therefore, we already know these homology groups. They are these reduced homology groups. As we learned, they are Z if the degree is the same as the dimension of the sphere and 0 otherwise. So this is Z if K is M and 0 otherwise. And this tells us what is reduced homology groups here, because they're isomorphic. And from Excision Theorem, we then learn what is the reduced homology groups of this pair U, comma U minus a point. So to summarize what we learned, here. We think what we learned from this long exact sequence and this isomorphism, we learned that hk of u minus x, consider reduced. Well, for relative, reduced doesn't do anything, so it doesn't matter. So this is isomorphic to z when k equals n and 0 otherwise. So we, remember this. So we can do. So similarly, we can do the same thing for V, for space V. And so let's take some point y, any point y in V. And similar argument will tell us that, so V is a subspace in Rm, so this will be Z when k equals m and 0 otherwise. Okay, we're almost done. And so we see that they are different, right? Unless these are different groups, unless n is the same as m. So let's assume. So by assumption, we have okay. This is a given, right? So there exist these. By assumption, this V and U are homeomorphic. This means there exist F homomorphism, for example, from U to V. Homomorphism, and we can always choose our choose some points x here and choose this its image. Let's choose this y to be the image of this point. So y was an arbitrary point in V, so we can choose it to be f of x. And then this tells us, so since it's a homeomorphism, this tells us there's an induced map between the relative homology groups is an isomorphism. And so these groups can be isomorphic. I mean, they should be isomorphic for all case. And this implies that indeed M must necessarily be the same as M. This concludes this proof of the theorem about invariance of the dimension. Okay, and okay, this is a place where I finish the course. Any questions?
Professor, do you have any sample exams or more exercise that we can practice before the final exam?
Yeah, I can put. Well, you can just look at the, for example, examples in the Hunter book. But I will put a few additional exercises on Moodle. Yeah, just to practice. I mean, I'm not going to give any points for solutions. But yeah, I can put some extra exercises to practice.
Yeah, thank you.
So in the exam, there will be 4 problems. So 4 problems, and they will all cost the same amount of points. So they all cost 5 points. Each problem will cost 5 points. But the problems can be and will be probably of a different difficulty. So of course, it makes sense to you to first kind of solve easier problems because they actually cost the same. So exam, there will be 4 problems. And so each costs 5 points, so they combine into 20 points. In general, and 20 is a maximum. So then you get a bonus from your, possibly a bonus from your homework. The maximal bonus you can get is additional 5 points, but the maximal total number you can get is still 20. And well, the problems will be similar to what you had in homework, but maybe kind of on one of the easiest, on the easier side. Kind of. You won't get problems of the difficulty level as the most difficult problems in your homework. So there will be most likely some problem about kind of prove something. About homotopy. Some question, kind of theoretical, prove something about like homotopy, homotopy equivalence. Then there will be most likely a problem about calculate pi1 using one compens theorem. And then there will be most likely a problem to calculate some homology groups using a long exact sequence. For example, calculate some relative homology groups using. Yeah, but of course, I mean, I haven't decided yet what you will have. This is most likely what you have, but there will be something else.
Professor, you mentioned that with the exam will be open book.
Yes, yeah, you can use anything, including internet. The only thing you cannot do, you cannot consult with other persons about the problems.
Okay.
In any way, you can cannot chat on online, cannot post questions on forums. Yeah, but any material you can find on the internet or whatever you can use. Yes, no issue. Just don't communicate with each other or with any other. But I wouldn't, I mean, it might happen that some of these problems, there exists a solution on the internet, but I wouldn't, you can try to find it, it's okay, but be careful how you actually spend your time. But I mean, most likely, you wouldn't be able to find exactly the problem I will post. I will tell you. I will use.
Sorry, I don't understand completely. We're allowed to carry book and that's it, right? But we have to attend, take the exam in the lecture hall.
So I don't know what I don't know where you will have exam. If you have a lecture hall or well, it doesn't really matter. Again, you can use well. I rely like if it's not going to be lecture hall. Well, it's going to be a lecture hall. You can bring any books or any computer or whatever, but just don't use it. Don't use these your communication devices to communicate between yourself. You can use them to search some material or have some like notes or whatever. Well, of course, if the exam is not going to be in the lecture hall, then I would have to rely on your honesty that you don't communicate with each other. Does it clarify?
Yes, Professor.
Yeah, so we will have tutorials, last session of tutorials where I explain solutions of the last problem set. But you can also, if you want some consultation about exam, you can well, either try to come by my office or schedule. If you want, you can schedule appointment and write me an email, and we can schedule an appointment, either online or offline meeting to meet. Any more questions at this point? Okay, if not, that's it for today.
Thank you.
Thank you.
Thank you.